Okay, in this video, we are going to look mostly at series. I'm going to define a little bit of what a sequence is, only to lead into the definition of a series because they're kind of related. And so we're going to look at how do you evaluate a series. So first, a sequence is a function that computes an ordered list of values. There's two types. There's the recursive and explicit. We're not going to go into detail about those. If you're interested in looking at them, they are in section 11.1 of the textbook. But some examples of sequences would be like 100, 200, 300, 400. That is a sequence. Another sequence, 2, 4, 6, 8, and so on. So that's also another sequence. In that section, it also talks about finite and infinite sequences. So if you're interested in learning more about the sequences, you can do that in 11.1 and look at that. Also in the same section, it talks about series, and this is what I want to focus on for this lesson. So the sum of the terms of a sequence is what a series is. So basically, we're adding up all of these values for a particular set of numbers in this sequence, and we add them all up. So this is what a series would look like, the notation. You have this symbol right here, which is the Greek letter sigma. It's the capital sigma, and it means to sum in mathematics. So that's what we use it for. It indicates that we are going to do some kind of a summation. We're going to add up a set of numbers. This bottom number is the starting value. So it lets you know what the variable is in the expression that you're going to replace the number with. So, and then that's the number that you start with. And the number on top is the number that you are going to end with. So that's the ending value. So this would look like 1 squared plus 2 squared plus all the way to the sum with the 100 squared. And just add those all up. You would read this as the sum of k squared for the values of k from 1 to 100. So that's what we're doing when we see this symbol. So let's take a look at another example. So here we are going to look at the sum of 3k for values of k from 5 to 10. So it's really important to look at that index. It doesn't always start at 1. And that's what the k is called, the index. And again, it doesn't always start at 1. In this case, it's starting at 5. And so 5 and 10 are our limits for the summation. So we start at 5 and we'll go to 10. And the 3k represents what they call the summand. Okay, so that's just the expression that we're going to be plugging the numbers into. Oh, again, this index can be any letter. K, I, N are very common. We're actually going to see an example a little bit later where I use a J. So you can really use any letter for the index. So here's the one that we were looking at, the summation of 3k from 5 to 10. So we plug it in to the k spot. So it would be 3 times 5. We start with the 5, and then 3 times 6, and then 3 times 7, 8, 9, and 10. So you just plug it in each time and multiply them by 3. So then you do the multiplication, and you add them all up. So when we add those all up, you get that this summation is equal to 135. We do have a finite series. These are the ones that we're going to be working with mostly today. They also have infinite series, and it's hard to see the infinity sign right here. So basically, this is what the infinite series is representing from 1 to infinity. This is probably what you're going to see a little more often in calculus, where you're going to be looking at limits and what this would converge to. So we're not going to talk about too much of this right now, but I want to make sure that you're familiar with how a series works and being able to do the summations. So another example that has a little bit more to it. So here we are going to do the sum of 2 to the k power plus 1 for k equal to 1 from 1 to 6. So you start by plugging in the 1. So this is the first one, 2 to the first plus 1. And then we go 2 to the second plus 1. And then 2 to the third plus 1. And so you just keep plugging in until you get to the 6, and then you stop. Then you evaluate each of these parts. So this would be 2 plus 1, so that's 3. This is 4 plus 1, so that's 5. This one's 8 plus 1, so that's 9. So you would go through and do every single one of them. You get these numbers and then add up these numbers. So it equals 132. So that summation expression or series is equal to 132. Now what we're going to do is look at some rules and properties that help us do some of these summations a little quicker, a little easier. Imagine like the very first example where it was 1 to 100. That is a lot to be adding up. There are some rules and properties that allow us to do it quicker. So on the assignment, I do have 2 problems that I'm going to want you to do this way, where it's the long version. They're short, like 1 to 6. I think it goes to 5 actually, so it'd just be 1 to 5 in the homework. So there's just 2 of them where I want you to show all of this work. And then you'll get to do a few of them using these rules and properties. So the different rules and properties. This first one, C in this case is considered a constant. And we're going from 1 to n. So the n just represents some number as our ending value. And so in this case, if it's a constant and you're just summing up that constant this many times, all you have to do is multiply n times c, and that would give you the summation. For the second property, if you have a constant times an expression, then you can factor the constant out to the front, do the summation with the expression. So the AI represents the expression that has the variable in it. Evaluate that, and then multiply by the C in the front after you do this evaluation. When you're adding 2 pieces, you can split them up. And we're going to do some examples of these so you can see how they're used. So do the summation for the first part of the expression plus the summation for the second part of the expression. Same thing with the minus, it works the same way. So you do the summation with the first part of the expression minus the summation with the second part of the expression. So these are some properties that allow you to simplify the expression a little bit for simplifying. Then we have some summation rules that are really helpful. And so you can use the properties that we were looking at above, plus these rules to help you simplify some series. So for this first one, remember the very first example I showed you was from 1 to 100 of I. So it's 1 plus 2 plus all the way to 100. Actually, I think it might have been the squared version. But that's still a lot. There is this expression that will equal the same thing. So someone has gone through, they've done the proof, they've shown that with an expression like this, if you do n times n plus 1 and then divide by 2, it will give you the exact same result. So if I have 1 to n of a variable, just a single variable like I, then I can use this expression. N is the end number value, so you would plug that end number value in there and calculate this, and that would give you the sum for that series. If it's an integer squared, as in this case, we have the integer squared, you would do n times n plus 1 times 2n plus 1 and divide by 6. This would give you the same result as this sum. For I to the third power, you would do the same similar kinds of things. There is this expression that would give you the same sum, n squared times n plus 1 squared, and then divide by 4. We're not going to go into all the big long proofs about this. You could probably find them in your textbook or look them up online if you are interested in seeing how that works and see the proof of it. What we're going to do now is look at how we might use these rules and properties to find the sum for a series and evaluate a series. So here I have 3 examples, and so we'll go through each of these quickly. So this is a constant, so I have the summation 1 to 50 for 12. So basically that means 12 plus 12 plus 12 plus 12 plus 12, and you would do it 50 12s. But if we use our property from the previous slide, we can just take however many times we're going to be using the 12, which is 50, and multiply by 12. And that would give us the sum. So the sum of all those 12s would be 600. The next one, we have 3K. So first we're multiplying it with a constant. So the first thing I can do is bring that constant out to the front. So let's look at that. That is this property right here. So we can bring that constant out to the front. So I'm going to take that constant, bring it out to the front. Then I have a summation of K. So K is just a single variable from 1 to 35. So now I can use the rule that was with the single variable. So let's go back real quick and just look at that. Okay, that was this first rule right here, where it's just the single variable. So I can do n times the n plus 1 divided by 2. So I'll show you what that looks like in this case. So n is 35. I still have the 3 in front. Don't forget that 3. And then it's 35 times 35 plus 1 divided by 2. So this represents this series. So I do this calculation. I get 630 and then multiply by 3. So it's 1,890. This one has the addition property as well. So there's a mix of things. So the first thing I usually like to do is if I'm adding and subtracting parts, split those up first. So I split those up first. Okay, so that summation, because of the plus, I can sum each part individually. And then if I look at this first one, I've got that constant in front again. So I'm going to pull the constant into the front of the summation. And then this is the variable squared. And remember, we had a rule for the variable squared. So we're going to use that rule for the variable squared. It was n times n plus 1 times 2n plus 1. So we are going to plug that in. So n plus 1, 2n plus 1, and divide by 6. So that was the expression, the rule. I still have the 3 in the front. Okay, so this summation is what's in the parentheses right here. And then after the plus sign, this summation, where it was from 1 to 10, and summing the 5 from 1 to 10, that's just summing a constant, so it's 10 times 5. So that mixes a couple of the different properties and rules. And then evaluate. So I evaluated what was inside the parentheses first and got 385. Then multiply by the 3 and add the 50. So the summation for 3j squared plus 5 is 1,205. So I'm going to post the problems, but if you have your textbook, you can just go straight to the textbook. It's on page 1004 to 1005. For 37 and 41, I want you to work it out the long way, like the first example or two. And then 71, 73, and 75 are just like those last couple that we did, where you get to use the rules and the properties. And if you have any questions, please send me an email and let me know.